Okey, Assalamualaikum semua dan salam sejahtera. Diharapkan semuanya dalam keadaan sihat dan masih bertenaga dalam mengharungi beberapa hari lagi sebelum final exam. Hari ini kita teruskan topik terakhir untuk kursus KM3443 iaitu berkaitan dengan stress and strain measurement ataupun dalam bahasa Melayunya pengukuran terhadap tegasan dan terikan. Okey. Okey, daripada hasil topik ini, kita akan merangkumkan beberapa aspek. Yang pertama, the basic. Okay, from the basic one, we learn what is a strain and what is a stress, what is the Poisson ratio, and a little bit about the solid mechanic and a stress strain link. And I believe that you guys is quite familiar with the stress and strain, right, during your second and first year. And after that, we go to the application in order from the measurement of a torque, force and pressure, we come out the solutions to find the measurement of the strain, and after that we go to the stress. Okay, and from in the strain measurement also we can divide the gauge into two, either they are in a single gauge ataupun kita gunakan multiple gauge. So they have a different between that and different applications and different procedure on that, and we will look at the example after that at the end of the topic lah. So we go to the fundamental of the definitions of the strain. What is strain? Okay, when we look at a textbook, we refer to the textbook. The definitions of a strain is elongation per unit length of a member subject to a applied force. So the strain is equal to delta L over L, which is the delta L here is the elongation or deformation occurs at the structure or beam when they are acting of the any loads, and L here is the actual length of the structure or beam. Okay, strain is a non-dimensionless, yes, because they have the units mm over mm, which is a dimensionless. It can be positive or negative, and direction must be defined. Okay. How about stress? In the textbook's definition, the stress is the internal forces per unit area. These internal forces maintain in equilibrium the applied external forces. So in other words, when you have the structure here and you have your external load acting horizontally, so from here if you look at a stress is equal to force over area, the cross-sectional area of the structure or the beam, right? And the unit of the stress is of course is Pascal or PSI. Okay, so this is how there are illustrate the calculation for a stress. When you have some structure and then you have your tension, you give a tension direction force acting on the structure. So from here, when you want to find the force, you want to find the stress is equal to the forces divided by the cross-sectional area of the structure. So you will get directly the internal stress acting on the structure or the beam lah, or the road. Okay, where will engineer care about stress and strain? What is the important to learn a stress and a strain, especially for engineer? Okay, this is because we need to understand the duty load occurring component, and also for a transducer construction using a working piece under load to measure a third property. Okay, we need to know the load, the capability of the materials undergo any kind of load, any kind of the applied load, in such a many way, right? uh, Information mengenai load ini sangat penting apabila kita bercakap mengenai engineering design. When we want to design something, product, a new product or something, a new structure, we need to know the capability of the structure to undergo any certain of load. What is the maximum, what is the minimum load that can stand of the structure. And it also is important in the engineering analysis, right? So you will learn about the finite elements, right? In the finite element they have a concept of the load, so you need to define the load in order to do the analysis. And then of course is in experimentation you have your load, and also for the measurement and a product development and product optimization. So all of this thing is related to the load. Okay, so this is the example application in industrial related to the load carrying component and structure. So from here you can see they have a pressure vessel here acting on the big sphere of the load acting on the pressure vessel. So you can see the shaft. Okay, the shaft, they carry movement of the rotational which create the applied load acting on the shaft. And also, and of course the last one will be a tower crane. All right, they will bring a very heavy compartment, very heavy components during the construction. So that is the type of the load acting on the structure. Okay, so the link from load to strain. Okay, so the load here we refer to as a forces, maybe a torque, pressure or vibration, and all of this load will cause a stress. Yes, of course. However, if you want to do the analysis, it's quite difficult for you. It's possible for you to calculate for the stress because we can't measure it, right? So for that stress, we have another option, because stress is causes of strain. So when we talk about strain, yes, we can measure that. Okay, is there a known relationship between stress and strain? Yes, absolutely, right? When you have a value, a data for the strain, absolutely you will get directly the value, the data for the stress, right? If you still remember, the relationship between stress and strain is equal to stress over strain, you will get the Young modulus of the material. So we have the value for the consistent of the Young modulus for any kind of material. If you have your variety of the value of the strain, so you will get the similar data for the stress, right? So the link between stress and strain that I mentioned to you before, this is the normal graph for the ductile materials for the stress strain curve. So from here you can see stress and strain are connected, yes, in the elastic region. So from here we can apply the Hooke's law according to the elastic region here. So if we want to find the gradient from the elastic region, the stress over strain, you will get the value for the Young modulus. Okay, this is what I'm telling you. Okay, this is from load they got to the stress, but you can't measure for the stress. You will go for the strain. The strain you will resist for the resistance change, and from that we can get the signal. Okay, this is how the process is undergo. Okay, you have your load, and then will cause a stress, and then stress is because of strain, and the strain will create the resistance change, and from the resistance change they are create a signal. Okay, we go to the example for the uniaxial extension or a compression. So from here, when we will make a cross section on the rod or beam, a truss for example, the stress, the axial stress acting on a truss here is equal to force over area, where A is the area cross section of the truss, right? I think this is very straightforward, and I really believe that you are already understand, you already learn about this thing during a solid mechanic and also a static, so I'm not worried about that. Alright, and then we go further on that. For a strain, if you still remember, you have your axial strain, you have your also your lateral strain. So what they are different between that? So from here, if you, for example, they have a root here, so when they have tension forces acting on the root, so from here when they are in the, they have the deformation occurs on the directions of the forces. So the that one, the L, delta L over L, we will get the axial strain. However, if they have a changes in terms of their size of the volume of the root with respect to the directions of the vertical one, so you will get the lateral strain, which is equal to delta D is over D, right? The N axial stress will be produced both axial and lateral strains. Okay, so from that, you have your axial, you know the axial strain, you have your lateral strain, so you will introduce the one term, one known is called as a Poisson ratio. What is the Poisson ratio? Poisson ratio is equal a ratio between a lateral strain over a axial strain. So you need to remember every material have a different Poisson ratio. Okay, for steel, the common value for the Poisson ratio is 0.3. So from that, when you have your modulus here, which is always positive for the Poisson ratio, you will get your last formula is equal to the lateral strain over the axial strain. Okay. Now we go to the another example, uniaxial bending. For example, a cantilever beam subject to bending. You still remember from solid mechanic how you want to find the bending stress, right? It's equal to negative or plus minus my over I. Okay, if you still remember the moment here, you calculate from here fx here, and then this is your y, which is the distance of the natural axis, and this is your I, which is your central moment of your inertia. So what they are trying to say here. Okay, so the sigma x here, this is the bending stress, is the axial stress at the upper and a lower surface. Okay, and also we go to the, we look at the another examples, which is in the biaxial stress case. Biaxial means that you have different, you have what you call, you have the different directions for of the load or of the forces, right? So for example here you can see they have the sigma x, and at the same time they have the sigma y here, different directions of the forces. Okay, this is how they are calculated for the biaxial stress case. So from here, if you have your tension, okay, in the x direction, and at the same time you have your tension at the y the direction, so both, when you combine all together the value of the forces, you will get the conditions in a biaxial, okay, which is we call as the biaxial stress lah. Okay, so from here, this is how they are calculated for the biaxial stress. Okay, so this is the strain at the y-axis, this is the strain at the x-axis for the what you call, for the second condition here. So when there's they sum up all of these things, so they will get the strain at the y directions is equal to this one, and also for the strain at the x directions. Okay, this is for a biaxial case. Okay, and also this is how they are mentioned to you. Okay, so and they are also rearranged. Okay, they make a rearrangement so we can use our strain to figure out of the stress. So we have what we call, you have two simultaneous equation here. So come out, you need to make it a rearrangement and substitution here and there. So you will get the sigma y is your main term right here with respect to the strain y plus a strain x, right? It's similar with this thing, the sigma x, the stress at x with respect to the strain at the x and also strain at the y. Okay, you can try by your own at your home, and in you make sure you will get this kind of results. Okay, this is the example for a strain gauge based on a transducer. If you know that the transducer is a device or equipment that can change from one energy to another energy. For example, if they have a very big ring here, which is from a torque transducer, so it will create a pressure. From here they will produce the electrical energy on that. Okay, this is just for example using the strain gauge based transducer. Okay, now we go to the resistant strain gauge. Okay, uh, every strain gauge adalah sensor untuk mengesan strain ataupun terikan yang berlaku kepada bahan. So oleh itu dia juga akan menghasilkan resistance, okay, pada setiap gauge yang digunakan. Okay, the measurement of the small displacement that occurs in the material or object that is subject to the mechanical load determine the strains. Okay, the ideal strain sensor will have a good spatial resolution. Okay, every strain gauge they have their different, they have their own spatial resolution, and then be unaffected by changes in the ambient temperature. Yes, and the third one, they have a high frequency response for a dynamic and a strain measurement. Okay, so this is the figures 2 is a detail of the basic strain gauge construction. So you can see they have the grip here, and then come out with the lead wire acting, the acting on the outside and the inside, and then they have a covered for the inner layer lah, and then the outer layer they have the encapsulating layer. Okay, we go to the metallic gauge. Okay, consider a conductor having a uniform cross-sectional area and length made of a material having the electrical resistivity rho E. For this electrical conductor, the resistance R is given as, so this is the formula for electrical conductor resistance. So the total change in R, we come up with this formula. Okay, the dependence or resistivity on the mechanical strain is called a piezo-resistant. It can be expressed in terms of piezo-resistant coefficient. Pi 1 is defined as this one. So when they are substituted on the top one, we divide by R. So with all the definition, the change in resistance may be expressed as this one. Okay, there's a derivation, the detailed derivation inside the books. If you prefer to understand that, you can go through on the books books that we refer, right? Okay, strain gauge construction and bonding. Okay, apabila kita ada strain gauge dan kita nak mengukur sesuatu terikan yang berlaku kepada struktur itu, kita perlukan ada bonding ataupun ada adhesive, ada sesuatu yang boleh lekatkan strain gauge kita, yang boleh kita install our strain gauge pada pada komponen tersebut lah. Okay, the gauge length illustrated in figures below is an important specification for a particular application. So if you can see from a figure 3 here, the construction of the metallic foil strain gauge, and then the most important thing from the component is the gauge length. So you can see here, okay, there is the gauge length oh sorry, this is the gauge length of the strain gauge, okay. The photo etched metal foil method is mounted on a plastic backing material. Okay, di mounted dengan plastic backing material for a bonding, okay. Okay, the variety of condition encountered in a particular application required a special construction and mounting technique. Okay, untuk kita nak implement our strain gauge pada komponen itu, ada beberapa conditions yang kita perlu ikuti ataupun teknik yang kita perlu ikut untuk memastikan we get the accurate result, we get the less accurate, the less what I call, the less errors in our measurement, okay. The first one is the design variation in the backing material. Insulate the metallic gauge from the test specimen and transmit the applied strain to the sensor. The second one is the grid configuration, and it is very important. As you can see from a figure 4, we has a different type of the configuration of the strain gauge. So from here, different configuration will come up with the different name. So from here, A here we call as the torque rosette. This is the linear, and this is a delta. This kind of configuration is quite famous during in the industrial in the industrial application. So D is we call as residual stress pattern. This is diaphragm. This is T, rectangular, and also H is the stack rosette, and this also is quite famous positions or configuration of the strain gauge in order to calculate or in order to measure the strain in the component, okay. Sorry. The third one is the bonding technique. How you want to connect, how you want to get a contact between your strain gauge to the surface of the material. So that's important for you to know what is kind of adhesive that available, okay, in order to get the 100% efficiency of your strain gauge, okay. The total strain gauge electrical resistance to create a sensor that is sensitive only to strain along one axis and therefore has a zero sensitivity to lateral and shearing strain. So that is what I'm trying to say to you, okay. We want to get the gauge that sense only to strain along one axis, okay, therefore have a zero sensitivity to lateral and shearing strain. So that is the more important, okay. The adhesive used in the bonding process and the mounting technique for a particular gauge and manufacture vary according to the specific application. So we need to use the special or the specific adhesive in order to get the bonding between our strain gauge and also to the surface of the structure or component according to the specific application. So it depends. If you want to put a strain gauge at the suspension, for example, so you need to make sure the adhesive bonding is very good in order to make sure the what we call the strain gauge is not tercabut ketika strain gauge itu beroperasi, okay. The adhesive bond serve as a mechanical and thermal coupling between the metallic gauge and the test specimen that I said to you before. The change in the resistance of strain gauge is normally expressed in terms of empirically determined parameter called as gauge factor. So we have a gauge factor in order to represent the change in the resistance of the strain gauge. So the gauge factor is equal to delta L over R over delta L over L. So delta L over L is the strain in A, and so the delta L over R is the changes of the resistance, okay. So the percentage error due to the transverse sensitivity on any material at any orientation in the strain field is calculated from this one, okay. When EL is the axial and lateral strain, VP is the Poisson ratio, and EL is the error, and KT is the lateral sensitivity of the strain gauge. Okay, don't worry about that. You don't need to remember, as long as you understand, you know how they are calculated and how they are the conditions where they are need to do in the what call in pada keadaan di mana, so it should be okay. No need to remember all the formula here. Okay, so the typical value of the transverse sensitivity for a commercial strain gauge is about negative 0.19 to 0.05. So the transverse sensitivity for the different strain gauge you need to know before you use that, right? Because it will affect the data that you will capture. Okay, figures 5 illustrate a plot of the percentage error for a strain gauge as a function of the ratio of the lateral loading to the axial loading. So from here, this is your lateral over your axial loading. So it will affect the value of your error with respect to the lateral sensitivity. So you need to define your strain at the axial and also a lateral in order to get the error, the less error on that with respect to the lateral sensitivity. Okay, now sebelum ni kita pergi metallic, so now we want to go to the semiconductor strain gauge. A semiconductor is the material that has the an electrical resistivity between that of the conductor and insulator. An external electrical field changes a semiconductor resistivity. Devices made from a semiconductor material are the foundations of the modern electronic, including radio, computer, telephone, and many others devices. Semiconductor devices include the transistor, solar cell, many kind of diode, including the light emitting diode, the silicon control rectifier, and digital and analog integrated circuit. This is just the introduction or the fundamental of semiconductor history. A semiconductor strain gauge, when subjected to a load, a semiconductor material exhibits a change in resistance and therefore can be used for the measurement of strain. Silicon crystal are the basic material for the semiconductor strain gauge. They use a silicon crystal for the basic material for the gauge. Okay, silicon is used to create most semiconductor commercially. Dozens of other materials are used, including germanium, gallium arsenide, and silicon carbide. A pure semiconductor is often called an extrinsic semiconductor. The conductivity or ability to conduct of a semiconductor material can be drastically changed by adding other elements called the impurities to the melted intrinsic material and then allowing the melt to solidify into a new and different crystal. This process is called doping. This is just for your knowledge only. Semiconductor material for a strain gauge application have a resistivity for 10 to power negative 6 to 10 to power negative 2 ohms meter. Okay, that's very good. A semiconductor strain gauge find their primary application in the construction of the transducer, such as load cell and a Fraser transducer. Okay, and figure 6 here shows the behavior with a temperature of the high resistivity p-type semiconductor. So from here you can see effect on the resistance for various impurity concentration for the p-type or semiconductor. You can see where they have a different percent of the resistance with respect to the increasing of the temperature. Okay, now we go to the strain gauge electrical circuit. Okay, for the electric circuit, a Wheatstone bridge is generally used to detect the small changes in resistance that are the output of the strain gauge measurement circuit. Okay, kebanyakannya kita menggunakan Wheatstone bridge lah, the basic electrical circuit in a strain gauge. A typical strain gauge measuring installation on a steel specimen has a sensitivity of a 10 to the power of negative 6 ohms kilonewton meter square. A simple strain gauge Wheatstone bridge is shown in figures below. Okay, the bridge output under this condition is given by, okay, when the E naught is the bridge output at the initial condition, the changes of E naught is the bridge diffraction associated with the changes in the strain gauge resistance, mu r. Okay, so this is the general equations for the bridge output under this condition lah. Okay, practical consideration for a strain measurement. Okay, now we go first to the multiple gauge bridge. The output from the bridge circuit can be increased by appropriate use of more than one strain gauge. Okay, consider the case when all four resistors in the bridge circuit of figures 7 represent a strain gauge. In general, the bridge output is given by this equation. Okay, so when you refer to the figure 7 here, if they come out with the if they have a 4 resistance or in one circuit, so from here the bridge output is given by this one, when E naught is equal to EI column by R1 over R1 plus R2 minus R3 over R3 plus R4. The R1, R2 is represented by the resistance mentioned here. Okay, the strain gauge R1, R2, R3, R4 are assumed initially to be in a state of zero strain. If these gauges are now subjected to strain such as the resistance changed by DRI, where I is equal to 1, 2, 3, 4, the change in the bridge output voltage can be expressed as like this. Okay, the summation of the difference of the E naught over Ri over dr. Okay, and then the basic working equation for a strain gauge bridge circuit using the multiple gauge is this one. Okay, the derivation, the detailed derivation you can get from the books given, so you can know why the strain 1, the what we call the resistance at the strain resistance 1 minus of the strain 2 plus strain 4 minus strain 3. So you will see the derivation, the detailed derivation from the books if you are interested, if you are curious about that. Okay, the second one, we go to the bridge constant. Okay, commonly used a strain gauge arrangement may be categorized by a bridge constant, okay, at a ratio which is the ratio of the actual bridge output to the output that will result from a single gauge sensing the maximum strain. Okay, so the output for a single gauge is calculated from this one. And why, however, for when more than one gauge is used in the bridge circuit, so the equation become like this. So this is how they calculated for a single gauge, and this is how they calculated for the more than one gauge. Okay. Okay, the apparent strain and a temperature compensation. What is the important for the apparent strain and a temperature compensation? Okay, apparent strain is manifested as any change in a gauge resistance that is not due to the component of strain being measured. Okay, let us examine how a component of strain can be removed from the measured signal. Okay, consider a beam having a rectangular cross section and subject to the loading condition as shown in figures below. Right, so you have your load here acting on here, so you have your rod here. Okay, the beam is subject to the axial Fn here and the bending moment, correct here. The stress distribution in the cross section is given by this one. Okay, this is how you calculate for your stress x. Okay, stress at x. Okay, to remove the effect of the bending strain, identical strain gauge are mounted to the top and the bottom beam. If you can see from the graph, okay, they are put the strain gauge up and down of the structure of the beam. Okay, why? Because they are want to remove the effect of the bending strain, and they are connected to bridge location at 1 and 4. The bridge output under this condition is like this. This is the general form for that, where the strain 1 is equal to strain axial 1 plus lateral strain at 1, and strain 4 is equal to axial strain at 4 minus with the lateral strain at 4. We subscribe A and B referring to axial and bending strain respectively. Sorry, the B is not the lateral, this is the bending, sorry. Okay, this is the axial and this is the bending strain respectively. For a single gauge experiencing the maximum strain, so you will get the result, the relation of the single gauge, okay, with the maximum strain. Okay, di sini kita nampak a common gauge mounting. Okay, the different positions of the strain gauge for some practical bridge gauge configuration. So from here, what is the compensation provided and what the value for the bridge constant will affect the positions of the gauge mounted to the structure or to the beam, right? So example, you can see if they have a single gauge, if they have one here, if they have a two gauge, if they are upper one and bottom one, so you can see the different on that and the different purposes for the gauge in order to calculate for the strain. Okay, now we go to the temperature compensation. Okay, differential thermal expansion between the gauge and the specimen on which it is mounted creates the apparent strain in a strain gauge. The temperature sensitivity of strain gauge is caused by a temperature changes in the gauge itself and the strain experienced by the gauge as a result of a differential thermal expansion between the gauge and the material on which it is mounted. Yes, correct. Okay, bila dah ada suhu memainkan peranan apabila adanya differential thermal expansion pada itu, dia sedikit sebanyak mengganggu the gauge and also the material yang mounted together itulah. Heating of the strain gauge as a result of current flow from the measuring device may be source of significant error since the gauge is also a temperature sensitive element. Bila ada sesuatu heat yang berlaku, ada current flow yang berlaku menyebabkan gauge itu kurang efektif. Mengapa? Kerana dia menghasilkan a source of a significant error. Because if we know before, the gauge is a temperature sensitive element. Using gauge of identical alloy composition as a specimen minimize this latter effect. So from that, using gauge with the identical alloy composition akan minimize the problem, they minimize the effect. Okay, figures 9, okay, shows a two-circuit arrangement that provide a temperature compensation from a strain measurement. The strain gauge mounted on the test specimen experienced a change in resistance caused by a temperature change and by applied strain, whereas the compensating gauge experienced resistance changes caused only by the temperature changes. As long as the compensating gauge experience an identical thermal environment as the measuring gauge, the temperature effect will be eliminated from the circuit. So from here they have a different different place for the compensating. So from here, so you can see they put the gauge in one at the top of the specimen of the beam, and the second one they put the gauge at the compensating at the another positions of the compensating gauge. So from here you need to make sure the both have a same material and temperature. Therefore the temperature effect will be eliminated from the circuit. Okay, now we go to the bridge static sensitivity. The static sensitivity of the bridge arrangement in figures 9.9a, okay, 9a here, okay, is calculated from this. This is how they calculate it for the static sensitivity, where of these conditions appear, and then the static sensitivity for the B. Okay, you can see the position of the compensating is the difference from A to B. okay, we'll get this equation from this general form in order to find the static sensitivity of the regimen. Okay, now we want to learn how we want to analyze the strain gauge data. The strain gauge mounted on the surface of a specimen respond only to the strain that occur at the surface of the test specimen, correct? The result from a strain gauge measurement must be analyzed to determine the state of stress occurring at the strain gauge location, correct? The multiple element strain gauge used to measure more than one strain at a point we call as a strain gauge rosette. Okay, the strain gauge rosette are commercially available in a variety of configuration, including gauge placed at angle 0, 45, 90 degree, or 60, 60, 60, 60, 60, 60, or 0, 45, and 90. So this is the figures 10 shows the biaxial strain rosette. Okay, this is just the example. So this is the single plate type and this is the stack type. Okay, they overlap each other. Okay, this is what they are trying to say. For the rectangular, this is how you can see they have a 0, 45, and also 90. This is the degree, the position, the configuration of the gauge, of the strain gauge. And A is the planar configuration and B is the stack configuration. Okay. Consider a rectangular rosette with the angle 0, 45, and 90 degree. Assumes that the major strain from the stack gauge are strain 1 from 0 degree gauge. So we can see, for example, this is a 0 degree. Okay, this is a strain 1. Okay, this is okay. From here, sorry, we refer to the strain 1 from here. Okay, this is your 0 degree. Okay, no angle achieved. And then strain 2 from a 45 degree gauge. So when they have the angle 45 here, so they come out with the position, the configuration of the gauge is here, which is the 45 degree gauge. And strain 3, which is the 90 degree gauge, oriented with the y-axis. This is the 90 degree, this is 45, and this is 0. This is a condition when they are stacked together, when they are intersect to each other. So from this major strain, the principal stress, you can calculate the principal stress, the sigma max or sigma min, and the maximum shear stress may be calculated as. So from this is the equation that you need to understand, that you need to remember in order to find the analysis of the strain gauge. Okay, so if you want to find the principal stress, the sigma max here is equal to this one, and then this is your sigma min, and this is your shear max. Okay, in order to find the value lah. Okay, now the last one is the angle. So if you want to calculate the angle between the x-axis and the maximum principal stress, and this is the equation that you need to use. Okay, so we go to the example before we finish our topic. Okay, a rectangular strain gauge rosette is composed of a strain gauge oriented at relative angles 0, 45, and 90 degree as shown in figures 11b. So this is how it is about. Okay, the rosette is used to measure a strain on the aluminum structure member when your E is here, your Young is here, and your Poisson ratio is here. The measured value of strain are given to you. This is the strain 1, the strain 2, and the strain 3. Determine the principal stress and the angle of the maximum principal stress relative to the axis. So you need to find the stress, the sigma max, sigma min, and also the theta. You need to find the angle. Okay, so what you need to do is just referring to the equation given to you. So from here you have all the value for that, so you just substituted it. So from E you have a 69, so you have already your strain 1 and strain 3. So you just substituted it and you will get the direct result of your sigma max, which is 2.13 megapascal. And I believe that if you try at your home, you will get also the value for the sigma mean, for the principal stress. You will also get your shear max and also your angles. Okay, I hope you can try and you will get the same result from here. Okay, I think that's all for our semester, for our this semester. This is your last topic for your courses, your course. I hope you can what you call, uh, you can do on your finals. Okay, best of luck for you guys. uh, Before we stop for this semester, I have something that I want to you guys do, which is the e-quiz 2. This is the individual assignment. Please submit your answer by 8th of July, which is after your final exam, in the UKM folio link. Okay, the questions I will upload it in the UKM folio, and then I will open the link in order for the submission. I hope you can still submit this e-quiz 2, because they have also the marks for that. Okay, I think that's all from me. Thank you guys. I wish you best of luck. Minta maaf jika ada salah sepanjang pengajian kita untuk semester kali ini. Okay, terima kasih. Assalamualaikum dan jumpa lagi. Oh, okay. Sorry. Ada ramai yang bertanya mengenai mengenai skim ataupun skema soalan untuk final. Okey, untuk pengetahuan semua, untuk KM3443 kita mempunyai 3 section, section A, section B and section C. Section A have 8 questions, so you need to answer all. Section B, you have 2 questions, but you need to answer only one. Same goes to a section C. They have 2 questions, you need to answer one only. Okay, the exam will be carried out 3 hours. Okay, for my part, it will cover all the topic that I teach, which is, if you still remember, about the signal, and also the second one I talk about the mathematical modeling, and the third one is the temperature, and last but not least about stress and strain. Okay, and for your information, my I think that's all. Best of luck for you. There has no for the tips. Yeah, just go through all the assignment, all the lecture notes, examples, in order to get some idea for you to answer the final. Okay, and also if you can refer the books, it should be fine for you. Okay, I wish you best of luck. Semoga berjaya. Assalamualaikum dan jumpa lagi.